Okay, let's get started. So as I mentioned last time, I'm still working on grading exam 1. Like I said, my goal is to get it great. I said next Wednesday. I mean, like, maybe I should just say Wednesday. Sorry, Wednesday. Because, yeah, I should have it graded by then. I do have, so just a little bit on the way that I grade. I don't grade on a student-by-student basis. I grade on a problem-by-problem basis, and I do that so that if I'm making any deductions, that they're consistent from student to student. Plus, it's easier for me to keep the problems in my head as I'm going through them if I'm just grading one problem at a time. So I'm going through it. I've got the first 2 problems graded. The third one I'm working on now. On it, ironically, probably the most quote-unquote difficult problem on the entire exam was the last conceptual question, because the last conceptual question was, what is the length of I plus j plus k? And a great many of you said 1, and that's not right. Because if I gave you the vector 2i plus 3i plus 3j plus 5k, how would you determine the length of that? You'd use the Pythagorean theorem, right? So what is the length of I plus j plus k? It's not 1. It's the square root of 3. So a lot of people said 1, and I was like, oh, that's not right. So that, I honestly, like point for point, was probably the most difficult problem class-wide. So, but it wasn't worth very much. So on par, the exam seems to be going pretty well for the class as a whole. So 3.1, or so 2.7 is graded, the solution's posted. 3.1 is being graded, that solution's posted. 3.2 is due today. 3.3, this assignment and this lecture is probably going to be among the most seminal as it relates to your understanding of moments, because what we're going to be doing is taking what we did on Friday and making it simpler by treating or dealing with situations where we're only concerned about moments in 2 dimensions. And we'll find that we can greatly simplify the math a little bit and sort of dispense with a lot of the IJK vector notation. Let me go to the lecture notes, but I'm actually gonna take also a step off to the side and talk a little bit about just moments in general. So first off, let's just make sure that we're all comfortable at this point with cross products. I think by now we should be pretty good with that. Particularly what's of importance today is just understanding how cofactor expansion works, because I'm going to use that definition to sort of simplify how moments in 2 dimensions work, and then make sure that everybody understands the formal definition of a moment. That if I have a force out in space and I am concerned about some point, we'll call this point 0, point naught, then the moment vector generated by that force is equal to r cross f. F being the force vector, the vector in IJK notation for the force in question, and r being a position vector that starts at the point in question and it ends at any point along the line of action of f. And I think we demonstrated that both with your homework assignment as well as the in-class example that we did, that if you perform 2 separate cross products with different r vectors, but as long as they're defined correctly from the point in question to the line of action, you will get the same answer at the end of the day. And I think that should be relatively clear by now. One of the things, though, that I don't think we did a good job with last time, and there's a reason for that, because I kind of want to reserve that discussion for today, is just what exactly this is, okay? So we had a homework assignment and we had a lecture last time where ultimately what we yielded was this, a moment vector. That's great. What is that? What does that mean? What does that represent? Okay. Well, I want to go back to a discussion that I had regarding forces and moments, and I gave you a new definition or a new way of thinking about forces. So probably when you walked in here, you were thinking, oh, force is mass times acceleration. You were thinking, Newton's laws, and you had a pretty solid understanding of what forces were, at least from that standpoint. But then I threw a different problem at you. I gave you the Jenga tower problem and the the situation with the mechanic trying to loosen that bolt in that machine. And we found that equilibrium and motion is not just about restricting objects from translation, but restricting objects from rotation as well. And so I said, okay, forces, another way of thinking about a force is any action on a body that increases its tendency to translate, whereas a moment is any action on a body that increases its tendency to rotate. Okay, so if I go up here, for example, and I look at the force vector, okay, so here's the force vector. It's negative 120I plus 96J minus 128K. So what this is just a notation expressing how much this vector is wanting to translate the body in the X, Y, and Z direction. So where it says negative 120I, that means negative 120 newtons in the X direction. So imagine I have a coordinate system, X, Y, and Z, okay? And I have negative 120. That means I'm wanting to translate at a magnitude of negative 120 directions in the x-axis, or 120 newtons in the negative direction of the x-axis. And this is how much I want to translate into y. This is how much I want to translate into z. Okay? So if that's what a force is, a moment is just that. It is an understanding of how much this force is wanting to cause rotation along the x, y, and z axis. And so we tend to express that in a force times distance unit. So you might think of it, a common gut feeling unit might be something like foot-pounds. We're dealing in metric, so for this particular problem, it's Newton millimeters. But essentially, this is how much that force is wanting to rotate the object about the x-axis. This is how much we're wanting to rotate about the y. This is how much we're wanting to rotate about the z. Okay? Now, the positives versus negatives, I think that probably takes a little bit of discussion. With forces, I think it's pretty easy. If the number's positive, it's just along the positive x-axis. If the number's negative, it's along the negative x-axis, as an example. But rotation's a little different, okay? Rotation, this sign convention, follows what we call the right-hand rule. And I think I had mentioned the right-hand rule a little bit, and I want to make sure that this is clear, okay? So the idea is that, and please forgive my horrendous artwork. I'm going to do my best. I'm not an artist. So that's the best you're going to get, okay? So the idea is, let's say we have a given axis in question, okay? If we take our thumb and we are on our right hand and we point that thumb towards the positive direction, okay, then the manner in which our fingers curl indicates positive moment, okay? So that's what the right-hand rule means, okay? So for example, this positive 28,800 times j, so take your thumb, point it in the y direction, and we are generating a positive moment of 28,800 Newton millimeters. So that means about the y-axis, we're wanting to rotate that much. Now, if we were pointing along the x-axis, what would happen is we would be pointing our thumb along the x-axis. Our fingers would be curling in the positive direction, but our magnitude is negative. So that just means that the moment is wanting to rotate in the opposite direction of the way our fingers are curling. Does that make sense? Is everybody okay with that? That's going to be a little bit important later and really relevant to what we're dealing with in this example, because what we're going to be doing is taking this and resolving it only to moments in 2 dimensions. Keep in mind, all these scalar quantities are the magnitude of how much a moment wants to rotate about a given axis. Okay, so with that, let's sort of get into the topic of discussion today. So we understand what cross products are. Well, we understand what cross products are. We understand what the formal definition of a moment is. But why am I talking about 2 dimensions? Like, shouldn't we be trying to generalize whenever possible in the land of 3D? Well, if I'm being honest, that may be how a mathematician and a physicist wants to handle things, is to try and develop formulas and methods that are as general as possible. And I think that is a solid approach. But I also am an engineer, which means I deal in the land of reality. And in most practical analysis situations, we try and idealize three-dimensional systems into two-dimensional models whenever appropriate. We do this all the time as engineers. Again, I'm a bridge engineer. Apologies to you mechanicals and biomedicals in the room, but I try and sometimes I relate things to civil a little more than I would like. But I think that even if you're a mechanical or a biomedical, you kind of get what I'm talking about here. So let's take a look at a bridge. So this is a three-dimensional system, okay? And to be clear, even in the land of civil engineering, when you're dealing with bridges, you have to address that three-dimensionality one way or another, all right? So this is a three-dimensional system, and what we tend to do as engineers is we tend to idealize that as a two-dimensional analysis problem. Now, there are some assumptions baked into that. With those assumptions does tend to yield a little bit of conservatism in your design, but conservatism in your design is not necessarily a bad thing, because that tends to mean that your design is safe, which is ultimately what we're after, okay? But notice how we're taking this problem and idealizing it into two dimensions. And we do this a lot in every aspect of engineering. I don't care if we're talking about a bridge or a machine or you name it. Taking problems and going from 3D to 2D is a very common approach, because 2D problems tend to be a lot easier to analyze by hand, and they tend to be something you can hang your hat on a little bit better. So what happens if we have moments in two dimensions? What happens to the math? Okay, so let's take a look at the formal definition of a moment, so R cross F, but let's assume there is no Z component. So we're only dealing in two dimensions. So our R vector is just Rxi plus Ryj, and then like plus 0k, there's nothing there. And then F, same thing, a magnitude times I, a magnitude times j, 0 times k. Okay, so what happens if I expand out the cross product? Okay, so what do we have here? So here's our definition of the cross product, and then what I'm going to do is I'm going to take this and I'm going to expand it using cofactor expansion. So I have the I vector, and then I knock out the rows and columns, and I get this. The j vector, knock out the rows and columns, and I get this, and then the same thing with the k vector. Okay, but let's check it out. What happens? Okay, so let's take the I vector. What happens when I determine this, when I compute this determinant? I get this times this, which is 0, minus this times this, which is 0. Okay, that's 0. What about this? This times this, which is 0, that times that, which is 0. All this cancels too. In fact, the only term that's left over is the z-axis. That's the only term that's left over. Okay? So, in fact, I can develop a very plug-and-chug expression for moments in two dimensions as follows. I can just say Rxfy minus Ryfx times k. In fact, what you will find in the land of analysis is that whenever you're dealing in problems in two dimensions, the resulting moment will always point along the z-axis. Like, imagine this table is my xy plane. So z is pointing up and down. So if I have a point in question, okay, and I'm restricting myself to the plane, and I have a force that acts on that plane, and here's the force, that force is going to want to cause rotation like this. It is rotating about this axis. My thumb is always going to point in the direction of that rotation, and in this case, my thumb is always going to point up. So as a result, what you'll find is that a lot of times when we're dealing with moments in 2D, we just dispense with the vector notation, because that doesn't really matter. Instead of writing the moment as a vector, some polyjump times k, we just deal with the magnitude of that vector, and we just compute that directly. So it makes the understanding of those moments a lot easier. And to be clear, we can also just recognize that ultimately moments are just defined as the magnitude of the force multiplied by the appropriate moment arm. And we're going to talk a lot about that in our example today. Does this make sense? All right, this example, I think, probably helps you understand what moments are probably better than any example that we'll do this semester. So I have an arm here. Let me pull up the notebook here while you all are copying this now. So I have a lever arm here, and I have a lever arm, and I have a 100-pound force that is being applied to this arm. It's being applied at point A. Okay. Now the arm is oriented at 60 degrees off the horizontal, and I have 100 pounds acting straight down. So we're going to determine a few things. We're going to determine the moment about that point, okay? We're going to determine the horizontal force that will be required in A to generate the same moment, and what's the smallest amount of force that would generate the same moment. And I think that this one example will probably really solidify what's going on with moments. It'll also help you understand what's the whole positive versus negative moments. Spoiler alert, we are going to treat, or we are ultimately going to find that for this problem, the moment is negative, okay? And I want you to understand what a negative moment means. I'm more interested that you understand what it means in 2 dimensions than you do in 3, because if you understand 2, the rest is just sort of an extension of that. I'll give you all another sec to copy this down, and we'll get to it. All right, everybody good? Okay, so ultimately what we're going to do is we're going to find the moment about point 0, point naught. If you ever hear me use the term point naught, that's just a point 0. So this is our point in question. So we'll say moments taken about point 0. Okay. The other thing that I want to go ahead and illustrate right now is this line right here. Okay, so that line that I've drawn right there, this is the line of action of F, and we're going to be able to make a number of observations about this line, and you'll notice how as we start going through the steps of this problem, you will see, wait a minute, isn't Dr. Mike doing this the more difficult way? Isn't there an easier way of doing this problem? And if you are making that observation, good, because that's what I kind of want you to see. Okay, now, as we remember, the position vector R, so in order to compute a moment, we need an R and an F, okay? In order to compute a moment, we need an R vector. R is defined as from the point in question to the line of action. And so what I'm going to do for the sake of our initial computations is I'm going to say that this is R. So that just the vector from point 0 or from point naught to point A, we're going to call that R. So we need to define these vectors. So let's do this. So compute the moment about O. And so the first way that we're going to do this is what I'll call formal definition. Okay. And so, in other words, R cross F. Now, we already defined that. We said that M naught is Rx Fy minus Ry Fx. But in order to do this, we're going to need vectors to define each of these two. We're going to need to actually define these. So here's the y-axis. Here's the x-axis. So let's start off with F. Can anybody write out a vector description for that applied load for this? Does anybody have a simple way of defining that vector?
0i minus 100j.
Exactly right. 0i minus 100j. So we'll say 0i minus 100j. Actually, is this too small? Do I need to write this bigger? Let me know. And we'll say this is in pounds. So I'll just stick the units here sort of off to the side. Now for the R vector is going to take a little bit of work, okay? So for the R vector, we know that we've got this sort of triangle like this. We know that this is 60 degrees, and we know that this is 24 inches because that's the length of the bar, okay? So this component here is going to be Ry. This component here is going to be Rx. So maybe a little bit of, trig tells me that Rx is 24 inches times the cosine of 60 degrees, and Ry is 24 inches times the sine of 60 degrees. So Rx, what's Rx? Twelve. All right, and what about the y-axis? That one's going to be a little messier. We'll say like 2 decimal places. 20.79. Do I have a second on that? Okay, good deal. So therefore, R is 12I plus 20.79J, and that is expressed in inches. So our resulting moment is going to be in inch pounds, like foot pounds, just we're not dealing with feet, we're dealing in inches. All right. So the first thing I'm going to do is, like I said, I'm going to use the formal definition of a moment. So let's check this out. So therefore, not the magnitude. So we're dealing in scalars right now. We're just dealing in magnitudes. So this is Rx Fy minus Ry Fx. Okay. So this is, let's see, Rx is 12. Actually, let's write out the units for this. Let's write it. 12. Fy is minus 100. Minus Ry is 20.79 inches. And Fx is 0. Did I get that right? Okay. So if I check this out, that term's going to give us 0, and this term right here is going to give us what? Negative 1,200? Negative 1,200. Okay. So first off, that's the answer. But I want to dig into that a little bit. Okay? Keep in mind that here's our coordinate system. So this is the y-axis, this is the x-axis, and then the z-axis is pointing this way, like out of the screen. Okay? So I'll sort of draw it like this, but really it's pointing out of the screen. Okay? So let's sort of go back to this right-hand rule thing. Okay? So this is the x-axis, this is the y-axis, the z-axis is this way. I'm going to take my thumb, I'm going to point it towards the z-axis. Okay? Now the way that my fingers are curling indicates positive bending moment, positive moment. Okay? So I would say then that based on this, that positive moment looks like this, right? In which case positive moment is, was that counterclockwise? Now we got a negative answer. Okay? So the way that I'm going to indicate this in 2 dimensions is instead of putting a negative, what I want to do is I want to say instead m naught is 1200 inch-pounds clockwise. Okay? Does that make sense? That if positive moment is counterclockwise, this moment is negative, which means it's 1200 inch-pounds clockwise. Is everybody okay with that? I want to stop for a sec and see if that makes sense. Yes?
How do you know to do the right hand rule in the y-axis or in the z-axis?
Because we're dealing in 2 dimensions. Okay? That's a great question. Okay? The reason that I knew to do the right-hand rule along the z-axis is because of this right here. Because if I have a force in 2 dimensions and I have a position vector in 2 dimensions and I expand out that cross product, every single time, I don't care what R is, I don't care what F is, the resulting moment is going to be along the z direction. Every time. That's why I knew to point along the z. That's a great question. Did that answer that? Okay, everybody else good with that? That was a really good question. Sound good? Now, let's just make sure that we're living in the land of common sense too, because, okay, I propose that this force generates moment that's clockwise. Does that make sense looking at the problem? I mean, look at the problem. Here's point naught right here. Here's 100 pounds over here. Isn't that what I want to rotate point naught this way? Like if you wanted to tighten point naught, right? Righty-tighty, right? You would yank this way. Does that make sense? Righty-tighty, lefty-loosey. So, again, technical language in the land of ignorance. Okay. So far, so good? Okay, now, what we just did is we computed moments using the formal definition. Okay? All right. Now, instead, I want to also compute the moment using the simplified definition. And the simplified definition is FD. Okay? Now, F, in this case, is just the magnitude of the force. And D is this term which we really haven't used up until now, which is called the moment arm. That M has one too many humps. All right, so what is the moment arm? All right, so I have point naught, some point out in space, and I have some force, and I have the line of action of that force. Now, I could define all sorts of position vectors, like I could have an R1, I could have an R2, I could have oodles and oodles of position vectors, and I don't care which one I cross. This with F, this with F, that with F, that with F. Doesn't matter. I'm going to get the same moment. Okay? But what is the moment arm? Okay? The moment arm is the distance from the point in question to the line, and specifically, it's the shortest distance from the point to the line. So, shortest distance is going to be that line right there, where this is perpendicular. This is 90 degrees, and that's 90 degrees. Okay? That is the moment arm. Okay? So going back to the problem, let's look at the problem in question. In this case, the moment arm is going to be this dimension. The distance from the point in question to the line, and specifically the shortest distance. Okay? So what we're talking about in terms of moment arm, this dimension is the moment arm right there. And what is D for this problem? What's that? RX, or in this case, 12 inches. Exactly right. Does that make sense? So, in this case, the moment arm is 12 inches, and so therefore FD is going to be 1,200 inch-pounds, and then observation tells us that it is rotating that point in a clockwise fashion, so M naught is 1,200 inch-pounds clockwise. So we get the same answer. I guess the downside, if you will, to using the simplified definition is that it does require you to observe the problem and go, is it rotating counterclockwise or is it rotating clockwise? You have to look at the problem and see which way it's rotating, okay? But I think that is an incredibly important skill to harness because that is going to be very vital later when we start looking at things like external support reactions. You're really going to need to understand how to do that in order to compute support reactions. I mean, I guess you don't need to, but it's going to make the problems a lot longer. So, does that make sense? All right, I want to stop for a second, see if anybody has any questions. Good stuff. Okay, this is good stuff. All right, let's go to some other questions this problem asked. This problem asked, okay, what horizontal force applied at A would generate the same moment. Let's digest that a little bit. What horizontal force applied at A would generate the same amount of moment? Okay. Let's draw our problem out. So, let's see. All right. So here's our bar. Forgive my artwork. I'm doing the best I can. So what we're trying to do in this case is apply a horizontal force. Now, I don't know how much, but I know I want to apply a horizontal force. And I want to do that in such a way that I generate a moment about this point of 1,200 inch-pounds. So how do I do that? Well, first off, let's just indicate that line of action. Just make sure we have that drawn out. And let's put some dimensions on this sucker. So this dimension here is 12 inches. And this dimension here, what was that? 20.79 inches. Move that down there. How do we do this problem? Maybe what we ought to do is we can handle it a couple different ways. Personally, I'm a simple guy. I like the simplified method as opposed to using the more formal approach. So M is FD. So the moment we know that's 1,200 pounds. We know that we need to solve for F, but in order for this to work, we need a value for D. Remember, what is D? It is a moment arm, right? Now, how do we define a moment arm again? It is a distance from the point in question to the line of action, specifically the shortest distance from the point in question to the line of action. What is that distance for this problem? 20.79. So therefore, what's that? All right, 57.7. Do I have a second on that? There we go. What do we think? Any questions? Now, I think the next problem sounds more complicated than it really is. You would be surprised how simple the next problem is. The last question that I asked on this one is, what is the smallest force? What is the smallest force that you could generate to generate the same moment? And I'm sure some of you are thinking, oh no, smallest means minimums. Minimums mean derivatives. Derivatives mean calculus. Come on, Dr. Mike, it's 8 in the morning. Coffee hasn't kicked in. Don't make us do any calculus this early. Relax. We don't need to do any calculus for this. I will level with you. There is some calculus that's coming later in the semester, but it's not so bad. But when I think of this, I'm thinking of the problem. What's going on with the problem? We have a bar, and we have a force being applied to that bar that's causing rotation. Now, you remember that picture I showed you of the mechanic, right? And notice how the bar was going this way, and the mechanic was pulling that way. Wasn't pulling like this or like that or like this. Perpendicular, right? If I had a bolt that I needed to tighten or loosen and I had a bar out here, I would apply that force perpendicular to that bar, right? Because that's going to give me the most effect. Make sense? That's where I'm going to get the most bang for my buck, as it were, in terms of actually getting the job done, applying that torque or moment. Again, moments versus torques, I could talk about that all day. It's really just a terminology question. So here's the bar, and I want to generate a moment again. And so in order to do that, the most effective way of doing it would be to apply that force that way. That's the most effective way of doing it. So the line of action is like this. So if I use my simple definition, I now, again, need a moment arm. What's that moment arm going to be for this problem? Say it again. 24 inches. That's exactly right. Okay? Because the moment arm is from the point in question to the line of action, and it's the shortest distance. We're talking about that being the moment arm. and D is the length of the bar, which is 24 inches. So this is 24 inches. So therefore, F is what? Say again? 50 pounds. So it's just kind of crazy that, you know, the original problem had 100 pounds of force generating this much moment, and I could do the same by applying half as much force, just applying it in the proper orientation. Interesting stuff, right? And while we're on the topic, one of the things that I'll say is that, so if you ever want to know what the difference between moments and torques are, I'm sure you can find articles about this. Really, it's just a terminology issue. I have tended to refer to torques more often when I'm dealing with things like torsion or mechanical design, whereas moments tend to be associated more with static equilibrium, which is why we use the term moment here. But if you're using the concept of torque to try and understand moments, not exactly the worst thing in the world because they're so closely related. Okay, any questions? So what we're going to do is I'm going to give you a homework assignment that's going to ask very similar questions like this. It's going to be, here's a problem. Give me a bunch of stuff about this problem. Tell me, what's the shortest distance for this or the smallest force for that. And if you understand that, again, I think that is the most important thing to understand about moments. Now, I'll tell you next time, we got a little bit of we're going to go back into 3D next time because we got a little bit of a wonky idea about how to determine moments about arbitrary axes. And in order to do that, we're going to need to use dot products. But that's another story for another day. That's all I got. I'm going to pull the QR code up again. Now, we'll see you all on Wednesday.